We're going to look at a couple of theorems for polynomials regarding zeros. So a zero or a root of a polynomial is a number c such that when we plug it into the polynomial, f of c is going to equal to 0. So to give you an example of a 0, let's say we have a polynomial function x squared minus 49. And we've factored these and solved them before, and if we solve this we got plus and minus 7. So we're going to look at 7. If I plug 7 in, 7 squared minus 49 is going to be equal to 0. So we would say that 7 is a root or a 0 of that polynomial. Give you another example. X squared plus 1. So roots can be real numbers and they can also be imaginary numbers. So remember that I squared was equal to negative 1. So if we evaluate this next polynomial at negative 1, I'm sorry, not negative 1, at I squared is negative 1, and we'd have negative 1 plus 1, which is 0. So I would be a root or a 0 of this polynomial. If I tried plugging 1 in, I would get an answer of 2. And if I get an answer that's not 0, then it's not a root. So 1 is not a root or a 0 of this polynomial. So we're going to look at something called the remainder theorem. So we're going to take a polynomial f of x and we're going to divide it by a linear x minus c. So it could be like x minus 5. The remainder, after we do the long division or synthetic division, is going to be the same thing as if we plug that number c in. So to give you an example, let's say we're going to take 4x cubed plus 5x squared plus 8 and we're going to divide it by x plus 3. Since it's a linear, we can go ahead and do synthetic division, which is a lot faster than polynomial division. And if we're going to do synthetic division, it has to be in the form x minus c. So to get it to fit that form, we could rewrite x plus 3 as x plus, sorry, not x plus, but x minus negative 3. Okay. So when we do the synthetic division, negative 3 goes on the outside, and then I got to be careful and put my coefficients in descending order. So we got the negative 4, a 5. Now I don't have a linear term. There's no x term in my dividend, so I put a placeholder in there. Otherwise, the synthetic division is not going to work. And then our final coefficient is 8, and we'll go ahead and do that synthetic division, bringing the negative 4 down, and then negative 4 and negative 3 makes 12. We go ahead and add them. 5 and 12 makes 17. And we'll go ahead and multiply again. Negative 3 and 17 makes negative 51. And we'll add 0 and negative 51 to get negative 51. And then we'll multiply negative 3 times negative 51, and we're going to get positive 153. And then we'll add 8 and 153, and we'll get a remainder of 161. So that's a remainder. So a remainder should be the same thing as if I plug negative 3 into the dividend. So let's plug it in. So we're going to replace the x's with a negative 3 in the dividend. And we'll go ahead and work that out. Careful about the negative signs. And we, in fact, get the same thing. So this allows us to check two ways what the remainder would be if I divide a polynomial by some linear term in the form x minus c. And this is going to be used in the factor theorem, which is going to say if this remainder is 0, I'm sorry, not the remainder, but if I evaluate it and I get 0, which means it would be a 0 of the polynomial, then when I do the division, I'm also going to get a remainder of 0. And that's the factor theorem. X minus c is a factor of f of x if I do that division and I have a remainder of 0. And give you an example, something real simple. If we take 4 and divide it by 2, 4 divided by 2, and if I take 2 into 4, 2 goes into 4 twice with a remainder of 0, so we would say that 2 is a factor of 4. So it works the same way with polynomials. And the factor theorem is going to say x minus c is a factor of f of x, which means is if I do the long division or synthetic division, then I'm going to get a remainder of 0. If and only if, which means it's going to go both ways, if and only if f of c is equal to 0, or that means c is a 0. So if I take some number, plug it into the polynomial and get an answer of 0, then x minus that number is going to be a factor. So we'll do an illustration of this. We'll take a polynomial 4x to the fourth minus 15x squared minus 4, and we're going to divide it by x minus 2. Okay. Now this one's in the form x minus, so when we do the synthetic division, it's just 2. And we'll put our coefficients in. So we have 4 for the 4x to the fourth. We don't have an x cubed, so we need a placeholder, so we're going to put a 0. And then the x squared term is negative 15, and we don't have an x term, so we're going to put a placeholder of 0. And then the constant 4, and we'll do the synthetic division. I bring down the 4. 2 times 4 is 8. Adding 0 and 8 gives me 8. 2 times 8 is 16. Adding negative 15 and 16 will give me 1. Multiplying 2 and 1 will give me 2. Adding 0 and 2 will give me 2. 2 times 2 is 4. And then we get a remainder of 0 when I add the negative 4 and 4. So the factor theorem says that if I divide that polynomial by x minus 2 and I get a remainder of 0, then that means 2 is going to be a 0 or a root, which means if I plug it into the polynomial, I should get an answer of 0. So we'll go ahead and do that. And then again, you need to be careful about the negative signs when you're working these out. So we do that multiplication, work it all out. We certainly get the same thing. This says we're a 0. This says we're a factor. If I have a remainder of 0, we're a factor. If I evaluate it in the polynomial and get 0, that means it's a root. Okay. So if it's a linear factor, you want to use synthetic division because it's way faster than long division. So we have the factor theorem. We had the remainder theorem on the previous, and then the last thing we're going to look at is called the rational root test. Sometimes we're going to have to come up with this number 2 and to check it. And the rational root test is going to tell us all the possible rational roots we might have. Okay. So we're going to be given f of x is going to be this kind of scary looking thing, ax to the n plus a to the n minus 1, x to the n minus 1 plus. And then the dot 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 means the polynomial continues, plus a1x plus a naught. A naught is this folk right here. Okay. And what the rational root test is going to say is it's going to be factors of a naught divided by factors of an. So potential rational roots will be of the form a naught over an. And sometimes it's called the PQ theorem. And in order for this to work, the leading coefficient and the constant, they have to be not 0. Okay. Then potential rational roots. It doesn't mean they're all going to be they'll all work, or maybe not any of them will work, but it gives us somewhere to start. Because if we have no idea, there's infinitely many real numbers, infinitely many rational numbers. The rational root test limits it down to not so many to check. It doesn't give us complex roots, so that might be a limitation too, but it will help us with rational roots, and for most of the problems we're going to do, we'll have some sort of rational root, and we'll be able to break down the polynomial and find all of its roots. The potential roots of that polynomial are p over q, where q is a factor of an and p is a factor of a naught. So p is the leading coefficient factors, and q, I'm sorry, I said it backwards. P is the factor of the constant number, and q is a factor of the leading coefficient. So let's do an example. 2x cubed, 9x squared plus 7 minus 8. Okay, factors of p would be the factors of negative 8. So we're going to take both the positive and negatives. So factors of 8 would be 1 times 8 and 2 times 4. So we'll get a 1, a 2, a 4, and an 8. Those are my factors of p, or factors of the negative 8. The q is, we're looking for factors of 2. So the only factors of 2 are 1 and 2, and then we'll take both plus and minus versions. Okay. Then to find all potential roots, they're going to be p over q. So we're going to take each one of the p's, and then if we have more than one q, then we have to split it up, and then all the p's over the 2. Now when I divide plus and minus by plus and minus, you're still going to get plus and minus. The nice thing about the first one is 1 divided by 1 is 1, 2 divided by 1 is 2, 4 divided by 1 is 4, 8 divided by 1 is 8. So we get those ones real quick, and we'll have the plus and minus variety. So I mentioned all the ones for the first batch. Now the second batch, I have 1 over 2, that would be 1/2. 2 over 2, which is 1. 4 over 2, which is 2. 8 over 2, which is 4. So we only need to list them once. So we have 1/2. And then we have 1. So we get 1 two ways. We get 1 over 1 and 2 over 2. Plus or minus 2. We get plus or minus 2 from 2 over 1 and 4 over 2. Plus or minus 4. We get plus or minus 4 from 4 over 1 and 8 over 2. And finally, we get plus or minus 8. Oops, let's go back. Plus or minus 8 for the 8 over 1. And these would be what I need to go ahead and check. So I would have to do synthetic division on those folks. So we got 2, 4, 6, 8, 10. We got 10 potential roots, which eliminates it from infinitely many down to 10, which is still kind of a lot. But what we're going to find with a lot of the examples we end up doing is a lot of times you only need to try 1 and -1, 2 and -2, and you might have to go a little bit further. But with the synthetic division, it makes it real quick. And what we're interested in doing is taking polynomials like this thing right here, which may or may not factor. Since it's a cubic, it has 4 terms, so we'd have to try to factor by grouping, and it doesn't look like it's going to factor by grouping. So we'd have to try something else, and this is something else that can help us break it down and find all the roots of it.